All right, everyone. So today we are going to be talking about manufacturing. I
Yay.
gave you a meme about OSHA because I think it's wonderful. So first off, kind of like the focus of today's meeting was centered around CAM. So what CAM is computer-aided manufacturing. So last meeting we covered computer-aided design. CAM is just sort of building on top of that. So with the CAD portion, you're actually figuring out, okay, what do I want my models to look like? And the CAM portion is how am I actually going to make this? Obviously, there's some things that maybe you wouldn't put in CAM. So like if you're like maybe bending sheet metal manually, basically all of the manual processes, you would not use CAM. Anything that you're going to be putting it into a machine that carries out what you're telling it to do, you're going to need some sort of CAM software. As the last bullet point states, some programs like Fusion already have CAM built into it. Some you need to basically export your CAD file to a separate folder, or not separate folder, separate
Holly, are
software.
you sharing something?
Oh my gosh.
Yeah, I was wondering. I was gonna ask when you said you're gonna start it with a meme and then didn't show anything.
My
I thought you
bad.
were just quoting
I
memes.
was so focused on the recording portion that I forgot the button next to it. Alrighty. There we go.
Hey, look at that! It's a presentation.
Yeah, we love presentations. Alright. Hello, welcome to my manufacturing video. Alright, so here's the meme so that you guys cannot be confused.
Beautiful. That's great.
What is CAM? So, as I said, computer-aided manufacturing, basically anything where you're not going to be having a person physically moving the tools around and utilizing the machines. The machines are doing all of the work for you. You're basically setting it up to go into the machine and then monitoring the machine as it's going through the process to make sure that nothing goes wrong. And yeah, so basically it sets up for additive and reduction fabrication processes primarily. So what that means, additive is like 3D printing. So if you have anything where you don't have material and then suddenly have material, you're building it up. That's additive. Reductive is exactly what it sounds like, exact opposite. You're taking material away, so you have a piece of stock and then you're removing material from it until you get your desired shape. So CAM software needs 3 components. So there's the software portion, which is what, as I said, Fusion would be providing right off the bat. And so that generates the tool paths. So it's good to keep in mind what machining looks like, and I would encourage you to get your own experience in our machine shops once they open back up, because it's really useful to be able to picture, okay, I have this piece of stock, how am I going to set it up on the machine? So how am I going to secure it? And then once it's secured, how am I going to actually machine out of it? And then there's the machinery portion. So once you've generated all the tool paths, it converts it into G code. M code is another type of code that falls in the similar language. And these are not necessarily, sorry, I might have skipped a step between machinery and post-processing, but the machines do take in that G code. And G code is basically just the machine's language. It's very common. It's not necessarily going to be fully standard, but it's pretty standard. If you have a particular machine and you're doing CAM for that machine, then just check the manual and make sure that it doesn't have its own language. And yeah, like I said, it gets sent to the machinery, and then it actually spits out a part for you. So when it converts it into this code, it creates these blocks of code. And the goal of this process is to make it as safe as possible. When you're talking about manufacturing, one of the most important things is cost. And so cost is going to be, how much time does this take? How much money does this take? And along how much money does this take? How many like hours of human work does this take? It kind of combines the two. And then, as I said, you don't want crashing. Crashing is basically the biggest thing that you want to avoid. So once you have like all of this, you can like optimize the code or whatever to be more efficient. Maybe you're saying, okay, I can actually feed it at a faster rate to spit this part out faster and still have it within tolerances. And I'll go into more detail in that in the next slides. But basically crashing is when the tool itself just sort of literally crashes into the part that you're making. And next slide. All right, so the big portion that I want to cover today is design for manufacturability. Basically, what that means is that you want to design a part that you can make, and you want to polish the process from as soon as it leaves the designer's hands, and even in the design process, all the way to when you have your final product and it getting into the consumer's hands. So this includes like the shipping processes and everything, but in our case, our biggest concern as designers is going to be, A, can I physically create this? You obviously can't have like a hole in the middle of like a block unless you're fabricating additively. And that is one of the benefits of 3D printing, is that you can make weird, intricate shapes. But things are a bit more limited when it comes to materials removal. Yeah. And then also some other considerations would be how tight your tolerances need to be. A lot of times people may not actually need a super high tolerance, but they'll just kind of throw on a tolerance that's standard to what they're seeing a lot of other times. And so if your tolerance doesn't need to be that high, the higher the tolerance, the more cost. So as I said, your main goal in manufacturing is lowering the cost once you've overcome, obviously, the basic criteria of actually being able to create this. And so let's say you want something, you only need it to like the 10,000th, or if you're doing something like pretty standard that's not going in like the aerospace industry, you're just kind of like making something in your house, maybe it just kind of needs to fit together. It doesn't need a super tight tolerance. So you don't need certain machinery that would be more precise. You don't need to, you can take higher depths of cut. You can maybe like just use rougher processes. And then also what materials should be selected. You can make something out of titanium, but it's going to take longer to machine. The titanium itself might cost more than, say, like a standard aluminum block. So definitely keep in mind what material is necessary. Kind of figure out how to balance between the cost and what is needed to perform. Like I said, titanium is just like a quick go-to example. Titanium versus aluminum, they have different properties. Something might call for aluminum where you really need it to use that material. Other things, maybe not. And then the final bullet there is what steps need to be taken to create this product. And as I said, that would mean like, okay, what machines do we need? What machines do we have? how many axes does the machine have, and I'll go more into that later. Just kind of keeping in mind, like, okay, if I were the person manufacturing this, how would I make it? And so this ultimately requires hands-on experience to really master the concept of and make it more intuitive, more, yeah, just like to keep it in the back of your mind less subconsciously. So I would definitely encourage you guys to do some machining, even if not on the mills per se, even just like standard things with like the saws, kind of figuring out, okay, how would I make this? How are these tools being used? All right, so first I'm gonna go into 3 really common machines. We have the mill, lathe, and 3D printer. I know when I first came to Cal Poly, I didn't actually know what some of these looked like. I didn't necessarily know how, I certainly did not know how to use them, because it's just not something that you necessarily have experience with unless you're in a machine shop environment. Sometimes people have just heard of them because they find machining cool or hang around a lot of people who use this stuff, but your average person may not know what some of these look like or how to operate them. And then within the mills and lathes, there is the manually operated ones, and then there are CNC. I will touch more on that later, but this is basically what they look like. So if you look at the mill, the head at the top holds, you can kind of, is there a way to show where my mouse is?
Yeah, we can see it.
You can see it? Okay, cool. So this part right here, this is basically where the tool is being held. And this is a manual machine. So in a CNC machine, you might be able to hold like multiple tools at once. That way you're not changing them out constantly. For a manual machine, you would have to change it out between each tool use. And then you're going to see 3 axes here. So axes are basically how many directions the machine can go. So in this case, it can go left, right, forward, backwards, and up, down. So that's 3 axes. And yeah, so the tool will be spinning really fast here. You'd secure the part somewhere on this table. And then you can work within those 3 axes to create what you want. Over here on the lathe, so before the tool was what was spinning and then the part was stationary. In this case, on the lathe, the part is secured and spinning, and then the tools are moved relative to the spinning part. That's the biggest difference. This is a lot nicer for if you have something round versus a mill, you would have to like actually program it to go around, which does work, but it's just nicer to use it on a lathe. And then, yeah, this is also manual. You do have this thing called auto feed in some manual machines, where basically you flip a switch and like the tool will move in like a constant path at whatever rate you set it to, which would be dependent on material and such. And then over here for the 3D printer, this is something a lot more people are familiar with. Basically, you have like this little spindle here of material that comes into this little head, and this moves relative here. Also, 3 axes can move left, right, up, down, and then forward, backwards. Like I said, this is an additive process. There are more types of additive processes than just standard 3D printing, but this is just kind of like the most commonly known one that people will think of when they think of additive manufacturing. And yeah, that material just kind of gets melted in whatever path that you so set it to. Do you guys have any questions?
Not really. Oh, when you were talking about crashing.
Yes.
That wasn't a software crash you were talking about, right?
No.
No.
Physical crashing, like into
Yes,
the tool.
physical crashing. So like if you had a part here, and then you just like dropped this into the part, or yeah, so basically you have the spinning little tool here, and then it just kind of like goes yeet.
Yeah,
Um,
I've been working on CNCs before when the person who made the machine code wasn't necessarily the person who secured the work in place to be CNC'd. And if you put your tool paths to navigate places, but you accidentally put the hardware to hold your work in the way, bad things happen. Do
Yeah.
not recommend. I have been the recipient of many flying drill bits and sparks from running full speed into steel bolts. So it's a bit of an experience to figure out how to hold your work without interfering with tool paths and stuff like that.
Yeah, it's funny too, because sometimes like you'll see like a vise that has like just a massive chunk taken out of the side, and you're like, ooh, someone had a bad time that time.
Yeah. Yep.
This was the site of a tragedy. Yeah, so do you have any other questions? And yeah, I guess the program crashing is an issue, but in terms of manufacturing, I think your biggest issue is going to be making sure that the tool doesn't ram into the part.
Yeah. I've never had a machine software crash, but doesn't mean it can't happen.
SolidWorks has crashed on me, but that's not while like you're running it, obviously.
Yeah.
Yeah. It was during the final too. That was a sad day. All right. So I'm gonna move on then. Please like just interrupt me if you have any other questions as I'm going through. I'll try to check in more. I know the last tutorial that I gave, I kind of just powered through. So I want to make sure that I'm checking in throughout this. All right. So, whoops, I mean to click that. All right. So I'm going more into machines. As I said, there's manual versus CNC. CNC stands for computer numerical control. You're going to hear a lot of acronyms. No one actually like refers to it by its full name because obviously that's much more of a mouthful, especially if you're like, hey, throw that part you're making on the computer numerical control. It's not nice. So just refer to CNC, but I'm providing these so that you kind of have an idea of where that originated from. As I said, machining axes is what directions is capable of going. 3 and 5 axes are pretty standard. 5 axes are really nice, actually. You don't get that all the time. And then I think I've heard of like having up to like 9 axes or something. Like you can do some crazy stuff, but you don't necessarily need that many for most parts. Obviously, we live in a 3-dimensional world, so that doesn't mean we're like transcending into a new dimension to create these parts. What that looks like more is like rotating ability. So if you have like a CNC and you're like, oh, this head can like go over here, like this part can like, having those different directions is more what it's referring to than actually like outside of the 3D realm. Yeah. RPM speed. These are just good things to keep in mind when you're analyzing cost, is how fast can we actually send this through? Can you like rough through some of like the bigger material removal parts in the beginning and then kind of do a surface finish at the end? What can the material handle? How fast, in the case of like where you're using like the auto feed, like how fast do you want to set the auto feed to? And even like without that, still like how fast is it moving relative to the part? Is it just going like this or is it going like this? That will make a huge time difference, especially when you're considering the mass manufacturing world where you're creating hundreds or thousands of parts. And then cutting surface speed, just kind of like, yeah, how fast it's going. All right, so some quick terminology. Never use the term lathing if you're talking to somebody who knows what they're talking about, they will cringe. The term is turning. That just means using a lathe machine, but it will only help you if you're talking to somebody who knows what they're talking about. If you say lathing, they might start to question your ability because you don't have the base terminology figured out. Milling is just milling. There's no special vocabulary with that, using the mill versus using the lathe. The part is what's being machined, and then the tool is like the actual bit that is going around and doing the work on the part. As I said, it may vary whether the part or the tool is spinning. That's the big difference between a lathe and a mill. And then jigs and fixtures, this comes more into that mass manufacturing realm as well. And if you have an intricate part, kind of weird shaped, you may want to make sure that, okay, I'm able to clamp it in this way. And if you have it where like, okay, I need a bunch of parts with a hole in this location, you can just kind of like set up a jig and then like piece it over and like just drill a hole. These are basically very nice for when you're getting into that mass manufacturing realm as well. Sometimes it will call for using one of these even if you're not making a lot of parts, just because of the way that it's shaped or whatever. All right, so now that you kind of have an idea of the manufacturing processes and like what tools, or I'm sorry, not what tools, what machines are available, are there any other questions? All right. So now you kind of have that base understanding. So you're going to want to set up your part on the machine. This is a huge consideration because you really need parts to be securely clamped when you have something spinning at thousands of RPMs, or even hundreds of RPMs. It's a lot of RPMs. It will fly if it is not securely clamped. So you want to make sure that you keep that in mind during your design process. In the case of clamping on the mill, you're typically going to have like some sort of vise, which is basically like just pressing the object together. A lathe uses more of a chuck. So what that means is basically like in more, what's the word? More circular, I guess, grip on it. A lot of times you'll see 3-jaw, maybe it'll be 4-jaw. There are different amounts of jaws, and basically each jaw is clamping from a different direction. So a 3-jaw, they would be evenly spaced out and they would move in and out this way. You also have a collet, which is more like what you would see on, trying to figure out how best way to describe that. A collet is less like 3 prongs and more like kind of, if you imagine like a cylinder around something and then you have slots cut into it so that it can like kind of grip around it and then fit in. That's more of what a collet looks like. So just in general, you're gonna have, once you have your vise or chuck, you're going to have hard jaw versus soft jaw. Basically what that means is hard jaw would typically be like a strong metal. Soft jaw could be wood, could be some sort of more rubbery material, more plastic. Basically, you're gonna default to hard jaw unless you have like a really soft metal or something where you don't want to mark it when you're clamping. So that way it still secures it without leaving marks or indents on the part. When you're setting up on a mill, you're going to want to make sure, basically tramming is making sure that it's level relative to the head of the spindle. And the way that you would do that is taking a dial indicator typically and just kind of running it over the top, seeing, okay, how parallel to the machining axes is this? Is it in line? Also, with the mills, you're going to, typically, if you just have like a standard vise, you're going to want to use parallel bars. So I should have included an image with this. Let's see, this one should go. So this is what the vise would look like, typically. And so this is actually probably a better picture. All right, so parallel bar will look something like this. They don't necessarily have holes in them like this. They will typically come in a set. They have different heights. As you have different heights of materials, you'll want to use different height parallel bars. This is what I'm looking for. All right, so you see this little like square block here. So you want the parallel bars so that basically it's only as high above these vise clamps as it has to be for you to be able to machine your part. Because the more that is clamped between these two pieces, the more secure it's going to be. So something heftier like this guy is just kind of getting clamped in there. Something small like this, you're going to want it propped up. Otherwise, if it's just down here at the bottom, you can't really reach that with the tool. And especially when you're going like across the ends, you're going to hit the ends of the vise there. So it's basically just to prop it up and make it reachable. But you don't want it to be so reachable that you aren't actually gripping the piece. Did that make sense to everyone?
Yeah.
Yeah.
Okay, cool.
Makes sense.
You're also going to be considering like edge finding, DROs or digital readouts. Basically, you'll have either a spinning bit or like a little like Ruby probe, and it'll just kind of find where the edges are and then offset the radius of that edge finder to figure out where like your origin is going to be. Then if you're creating holes with drills, you're going to want to consider center drilling or pre-drilling. Center drilling, basically, it's just making a smaller hole. That way, when you're drilling, the center is already established. Because if you don't center drill, then the head, while it's trying to dig down, the friction causes this potential for the tool, the end of the tool, to actually walk around ever so slightly. And then it may not actually be center with where you wanted the hole to be. So you'll just kind of like do a little tap down there. Pre-drilling is much more applicable for like if you're doing like screws in hardwood. Basically, it's creating a hole where you would want your screw to be. That way, like the screw kind of like some of the materials are already removed, but not so much that it just like falls in. Also keeps it in line. And then, yeah, you're also going to want to consider every tool that you use. You can have a ton of different tools available, but you want to have as little shifting between tools as possible. So because every time you change a tool, you may need to change the collet around the tool if it's like manual especially. And the collet is basically like if you have an end mill for the mill, it will fit in there as well. There's also the collet bit for the lathe, which I mentioned before. Yeah, so these are all just things to keep in mind of like when you're actually setting up the part. I've had some people design parts for me to make, and then there was actually no way of gripping it. So it's good to keep in mind like how it's set up on the machine, because like I said, once you have it on the machine, there's some parts that slow it down, but a lot of that's going to be like figured out by whoever's manufacturing it. So they'll kind of figure out, oh, this is the speeds I need to use, blah, blah. But on your end, if you can make their life easier by making a part that has edges to clamp by, that's helpful. All right. And then as far as tooling, so when you have like the bits that are doing the cutting, it's common to see high carbon steel, high speed steel, and tungsten carbide. I think are probably the three most common. Basically, the main difference is that like some of them you can feed into the part faster, just because it's less likely to break. Obviously, the price of these tools are going to be varying, but they do potentially increase your ability to work with certain materials that are harder to work with. Do you guys have any questions before I move on to like the actual tools?
No.
I think I'm all right.
All right. So as I said, this is a dial indicator. You can also use these on lathes manually to like tell how far from the edge of the part you're going, let's say. I don't necessarily need to teach you guys all like how to machine. I just want, my goal in this talk is just to kind of give you an idea of how people are going at it. But it's good to know like what these things look like and what they're used for as well, even if you're not necessarily using it yourself. Now, as far as like mill and lathe go, typically you'll have your end mills for the mills. This is flat nose, ball nose, bull nose, and chamfer. You can see that the bottoms kind of have different shapes. What varies an end mill from a drill, I should first specify, is that a drill, you're typically going to have this little cone down here. So this bottom of this like flat nose end mill, you can take it across the top of a surface, which is called facing. If you're not like, yeah, it's called facing to just go off the top. So you can do that with an end mill, which you would not be able to do with a drill. So it basically is how you use that bottom portion. Ball nose has more of a curved edge, so if you need more of an inner radius there, that's nice. More of a contour. Yeah. And then for the lathe, you typically have right hand and left hand tools. You also have one that looks more like a center, but basically, I forget exactly how they were named. I think it had something to do with like whether you're turning it right or left, but it also may have just been how it fits in your hands. But yeah, the direction that it's facing. So this one you would use more for facing off something on the lathe. So if you want to go across this edge versus going along this direction. And I have a little picture here that kind of shows like what the edges look like as well. All right, and then this is what the center drill looks like. I mentioned you may want to center drill before you actually drill. This is just to keep it centered. Drill bits, there are some drill bits that are not fit for metal. Yeah, mainly because they're more designed for wood or softer material like that. Yeah, as you can see, they come in a bunch of different sizes. There are different sizing, sizing groups, so like metric. They have letter drill bits. There's a lot of different types. And they, yeah. So generally, if you're making a hole, let's say you want to make sure that it falls within a standard drill bit size. Otherwise, you're going to have to do some weirder stuff. Boring tools and reaming tools, both of those basically do what the drill does, except it's not that initial cut. It's more like a finishing to hone in like the exact diameter that you want. Makes the inside really nice. It's not always necessary though. Now, as far as like screws go, or like bolts, anything with that sort of edge, typically you'll use taps and dies. There are some other like machining methods that you can take, especially on the lathe. There's a special like tool head that you can go across the outside at a certain feed rate, and it will basically spin the thread of your bolt or screw or whatever onto that. Taps go internally to a hole, dies go externally to a hole. And then, as I said, the edge finders tell you where the edge of the material is. This part here spins really fast, and then you can see basically what will happen is like that centripetal force is keeping it spinning around. This is tied in with a little cord right here that you can't really see. So imagine this part spinning around the outside very fast. You can see there's like the cylinder here, and then there's like kind of like a wider cylinder from the other part moving around. As you get closer to the part, it will start to look linear, and then you just do like the tiniest increments until it throws it off center, and that's where you mark the origin, and of course offset from that by whatever amount this radius is here. Otherwise you'll be measuring from the outside of this rather than from the center. All right, and then parting tools, these are nice for lathes. You have to feed it slower, so I'm not a huge fan of using them personally. If I can get away with it, I'll typically use some sort of saw, but parting tools do allow for you to, as the part is spinning on the lathe, it just kind of like cuts through until it's off, and then you can potentially do some sort of smoothing process on the end if you would like that extra bit. Do not forget that coolant is an important part of this. These things are spinning really fast. The tools get really hot. It does help a little bit as well with like just the way that it's interacting with the surface. But I think like the biggest thing that comes to mind for me is if you have this tool that's going super, super fast against this metal, it'll get pretty hot, especially if it's a harder to cut metal. So it's important to remember that you're going to need to cool that part. Otherwise, the chips may stick to the end of the tool. It may mess with some other stuff. It's just not a good time. So you want to keep in mind like how these things are going to work. As I said before, when you're designing, material selection is very important. Not only do you want to design for the part that you're making, but you also want to keep in mind somebody's going to have to make this. I should not throw an Inconel part at them unless I have to, because it is going to get really hot. They're going to have to go through a lot of tooling bits. Some tools have like replaceable heads at the end of them, so like you could go through those potentially fast. Yeah, do you guys have any questions?
No.
Cool.
No, that's all good.
Cool. All right.
That
was cool.
We had the collection of melted things from people who had forgotten to turn the coolant back on after checking something on the CNC.
Yeah, coolant is very important.
Very good. Do not forget.
Do not forget. Yeah, I think CNC you're more likely to forget about it than on a manual machine, because like as you're working you'll be like, hey, I see smoke. Or like, not necessarily, no, the smoke comes more from the coolant, but you'll be like, hey, this is weird.
Yeah.
I guess more is the case. Yeah, this is just kind of an overview of all of the titles that I touched on. If it sparks any memory of any other questions. Alrighty. Thank you.